Okay. Good afternoon, everybody. My name is Ossi Hahtela. I work as a senior research scientist at MIKES in Finland. The topic of my presentation today is thermal conductivity measurements of thermoelectric materials, especially using 3-omega method. As you may hear, my sound is not at its best today because of the flu, but I hope that the voice will last throughout this presentation. So here's the content of my presentation. I start with giving a short introduction and motivation to this work. I'll show you as reference two traditional ways of measuring thermal conductivity that are traditional steady state technique and also the laser flash method. And the main part of this presentation will be about 3-omega method. How this method works, what kind of requirements it sets on the samples and the measurement devices. Also, the measurement setup that was constructed at MIKES. I say a few words about measurement of different kinds of samples, dielectric samples, conductive samples, and thin film samples, and also show the measurement uncertainty analysis we have made for the 3-omega method, and finally do some summation. As you have already heard today, thermal conductivity is one of the key material parameters that determine the efficiency of thermoelectric materials. As you can see from the equation of the figure of merit, the lower the thermal conductivity is, it gives possibilities to reach higher figure of merit value. At present, the performance of the thermoelectric materials is limited by the available materials. In this field, there's a lot of activity in developing new materials, and one potential way to do that, to reach lower thermal conductivities, is to use nanotechnologies, to utilize thin films, nanowires, and nanopowders. But in development of new materials, and so that we can reliably compare new materials, we need, of course, accurate methods to determine the material parameters. Thermal conductivity of good thermoelectric materials is typically very low. I listed here a few materials so that you can get a figure of what kind of numerical values different kind of materials have. Copper, of course, have very high thermal conductivity. We have oxides, metal alloys that have somewhat lower thermal conductivity. Bismuth telluride is very well known thermoelectric material which have quite low thermal conductivity. Borosilicate glass is here because we used it as a reference material when we tested and characterized our 3-omega measurement system. Printed circuit board has very low thermal conductivity, and gases, of course, have very low thermal conductivity. Thermal conductivity depends on material's structure, its phase and temperature, and also if material is anisotropic, like very many of the new sophisticated materials are, the thermal conductivity depends also on orientation, in which direction we are measuring the thermal conductivity. There's quite many different methods to measure thermal conductivity. Some of them are transient, some of them are steady state, and typically each method is suitable for a limited range of materials depending on the thermal and mechanical properties, and of course the temperature range which we are going to measure. But one common point to all measurements is that good relative accuracy is very difficult to achieve. First, have a look on the traditional steady state technique, which has been used for measuring thermal conductivity of bulk samples. In this equation, this is pretty much what the definition of the thermal conductivity is. We can measure a bulk sample if we know the dimensions of the bulk sample. We heat other ends of the sample so that we get a known temperature difference over the sample, and then we need to know the transmitted heating power. And it's in paper it looks pretty simple method, but in practice it might be very difficult to determine the heating power accurately because there's typically heat losses because of the radiation and through the measurement wiring and support structure. So this method needs quite well-engineered experimental setup in which there's good thermal shielding and good thermal anchoring. Typically, vacuum environment is required, and also the sample dimensions are needed to be determined accurately. And typical accuracy with this technique is typically about 10% at best. Then a few words about laser flash method. It is non-contact transient method that have been used both for bulk samples and thin film samples. Typically, the sample is kind of disc-shaped with diameter of 10 millimeters larger. The one end of the sample is heated with a short laser pulse. This heat goes through the sample, and the temperature of the opposite phase can be monitored, for example, with infrared detector. This figure shows the temperature measured of the opposite of the sample, and the important measure is the time that the temperature needs to reach the half of the maximum value. Then using this equation, you can determine the thermal conductivity, but only if you know the density of the sample material and specific heat. So you need to determine those separately or use some numerical values found in literature, but for many new materials, there might be no available such information. Okay, then to the 3 omega method. This method was developed by Cahill et al. About 25 years ago, and it was first used for isotropic dielectric bulk materials. But lately, extensions of this method have also been used for thin films, down to thickness of a few tens of nanometers. It's been used with superlattice materials, nanowires, nanotubes, and even liquids and gases. The benefit of this method is that only a small part of the sample is heated, which minimizes the radiation losses. And also because only a small part is heated, it's a relatively fast method. You don't have to wait for a long time for the whole sample to stabilize. And also you can quite quickly measure a wide temperature range. On the other hand, this method requires sample preparation. You need to pattern a thin film on the sample using, for example, microlithography. So in this method, you need to deposit a metal heater strip on the sample, and typically in our measurements we have used gold as a heater material, about 100 nanometers thick, 50 micrometers wide, and the heater strip is deposited using thermal evaporation through a stainless steel mask. Here you can see the configuration of the such metal heater strip. You have contact pads for electrical feed-through and also pads for measuring the voltage over the strip. So we put a AC current at angular frequency 1 omega through the strip, which makes the temperature of the strip to oscillate at double of that applied frequency due to the Joule heating. And typical heating powers are quite low, about 1 to 10 milliwatts. This figure shows the cross-section of the sample plus the metal heater strip. The heat induced by the heater strip diffuses into the sample material, and the thermal penetration depth, so how deep the thermal waves penetrate into the sample depends on the applied frequency. So at low frequency, the heat has long enough time to penetrate deeply into the sample, and at high frequencies, the thermal penetration depth is much smaller. The amplitude of the temperature oscillations at the heater strip depends on the heating power, the geometry of the heater, and also thermophysical properties of the sample material under the metal strip. And typically, we chose the strip material so that the resistance depends also on the temperature, and that means that also the strip resistance starts to oscillate at 2 omega frequency. Now, the voltage that we measure over the heater strip has both 1 omega and 3 omega components, and that gives the name for this method 3 omega method. So the analytical model for the temperature oscillations at the heater strip is given by this equation here. It has both real and imaginary parts, but what is important in this method is the real part that depends on the natural logarithm of the applied frequency. The temperature oscillations can be measured by detecting the third harmonic voltage component, and in practice you measure this 3 omega voltage at several different frequencies. And as you can show in this figure, which illustrates the porphyroid glass sample measurements at 3 different temperatures, there's nice linear behavior of the temperature oscillations as a function of frequency. If we combine these two equations here, we can experimentally determine the thermal conductivity from this linear slope of the temperature oscillations according to this equation here. So the S here means the slope of the curve. This model assumes that thermal penetration depth must be larger than the width of the metal strip. Also, the thermal penetration depth must be smaller than the sample thickness so that the heating effect doesn't go too much over the sample, or there might be also reflections from the boundary line. Also, typically the thickness of the heater strip is very small, so that the influence of the heat conduction through or via this metal strip can be neglected. And also the measurements must be performed at the sufficient range of frequency so that we get this kind of nice linear behavior detected. Here you can see some parts of the measurement configuration that was constructed at MICAS. Here's once again this metal heater strip configuration with line width of 50 micrometers, and the length of the heater line is determined as a distance between the voltage measurement pads. To detect the third harmonic voltage component, we use so-called common mode subtraction method, in which this AC signal that is heating the heater strip, the same current is going also through a reference resistor, and the value of the reference resistor is adjusted to be equal to this metal heater strip resistance. So if we use a lock-in amplifier in a differential mode, we can get rid of the dominating 1 omega component, which is typically 1,000 times larger than the 3 omega component. And also this common mode subtraction method makes it possible to use a voltage source to heat the sample instead of a current source. Here's the measurements probe that was constructed for high temperature thermal conductivity measurements. Here you can see the sample, which is butterfloat glass in this case. The sample holder is made from machinable Makar ceramic. Copper nickel measurement wires are guided through a vacuum flange and through arsine tubes. Spring probes are used for giving the electrical contact for the sample, and also these spring probes keep the sample in place during the measurements. And also there's an additional PT100 sensor chip so that we can monitor the temperature of the sample during the measurements. If the sample material is dielectric, we can directly deposit the metal heater strip on the sample. We tested our measurement system first with borosilicate glass sample. We knew the thermal conductivity value from the literature. We measured this sample from room temperature up to 625 Kelvin. And as you can see from the results, there's nice agreement with the reference value. In this case, we determined the average relative uncertainty to be about 5%. The other curve, with open triangle symbols, this is the same sample measured with so-called Kapton film method. I'll say a few words about that later, but it is just good to note that the measurement results are very identical in both cases. Yeah. Okay, if the sample is electrically conductive, we need an additional dielectric isolating layer between the sample and the metal heater strip. There's many possibilities to how this dielectric layer is provided. One simple way is to use dielectric films that are deposited using, for example, chemical vapor deposition or atomic layer deposition or sputtering methods. Typical materials are, for example, silicon nitride, silicon oxide, or aluminum oxide. You can also use spin coating of some more exotic materials for this purpose, for example, different kind of epoxies, photoresists, or also liquid aluminum oxide. However, we noticed in this work that some sample materials are quite difficult in sense of using these traditional deposition methods. The adhesion of the dielectric layer might be so poor that the dielectric layer stripped off, or there might be a kind of pinholes through the dielectric layer so that there was more or less current leakage from the metal heater strip to the sample material. To avoid these problems, we started using Kapton foil as an isolating layer. So in this case, the Kapton foil works as a substrate for the metal heater strip, and it also provides electrical isolation for the measurements. So we measure thermal conductivity through the Kapton foil in this case. One thing to remember is that using this kind of method, you need to take care that there's good thermal contact between the Kapton foil and with the sample material, and we used a thin layer of silicon-based thermal paste to make care that there's good thermal contact. Another approach that we used is that we again use Kapton foil as a substrate for the metal heater strip, but now we add another dielectric layer on top of the cold heater strip and put the measured sample on top of that dielectric layer. Now there's some restrictions what kind of sample materials we can measure, because some of the heating may go to the capton, but if the thermal conductivity of the measured sample is much larger than thermal conductivity of the capton, most of the heating will be diffused into the conducting sample, and the capton won't make harm for the measurement. This slide shows measurement of bismuth telluride sample using 50 micrometer thick capton plate. Here you can see the temperature oscillations measured at two different temperatures. And as I showed you before, the thermal penetration of the heating effect depends on the applied frequency. If the frequency is very high, the thermal penetration depth is very small, and the heating takes place only in the capton film, and we effectively measure only the capton film. So we need to adjust the measurement frequency range so that we can be sure that we measure the sample instead of the capton film. Here's the measurements of two other conductive samples, the isotan metal alloy and bismuth-doped lead telluride, that were chosen as a reference material in this project. Isotan sample was measured using capton plate and putting the isotan sample on top of the cold heating strip. We found two reference values from literature, and according to those, our measurement results are in quite nice agreement. We measured the thermal conductivity from room temperature up to 400 Kelvin with average relative uncertainty of 8%. Here's the measurement results for the bismuth-doped lead telluride samples. We had 3 samples that were originating from the same fabrication batch, and as you can see, the results are quite nice agreement with each other. And this time the average relative uncertainty was 6%. Three omega method can also be used for thin film samples. By thin film samples, I mean samples, films with thickness of 1 micrometer and below, because there's restriction that the thickness of the thin film should be much smaller than the width of the heater line, so that heat flow through the thin film is mainly one-dimensional in the cross-plane direction. In such a case, and if the thermal conductivity of the measured thin film is small if compared to that of the substrate, the thin film behaves just as a thermal resistance, and the temperature drop across the thin film can be seen from this equation. And the essential part also is that this thin film produces only a frequency-independent increase in the temperature oscillations and no change in the slope of the measured curve, so that we can use the mathematical model that was showed you earlier. So in order to be able to measure thin film, we can use this kind of measurement setup. We first measure the thermal conductivity of the substrate material. So we get this kind of temperature oscillation curve. After that, we measure thermal conductivity on top of the thin film. There will be frequency-independent temperature increase in the measurement slope, as you can see here. So the slope will be stay the same. And from these two measurements, you can calculate thermal conductivity of the thin film. Then a few words about measurement uncertainty analysis. in practical measurements, we use this equation for calculating the thermal conductivity. The potential error sources or uncertainty sources are listed here. First of all, there's the temperature dependency of the heater strip resistance, which have been determined by measuring the resistance value of the heater strip at different temperatures. The temperature dependence is typically quite nicely linear throughout the whole temperature range, and we can determine the temperature dependency quite accurately. We also need to measure the voltage at 1 omega over the sample so that we can determine the power that we are used for heating the sample. We use also lock-in technique for measuring the 1 omega voltage component, and that is typically quite accurate also. Then one parameter is the length of the metal heater strip. The length is determined by the microlithography, by the mask that is used in the thermal evaporation of the cold metal heater. Also, we measure the average resistance of the metal strip, and resistance measurement is typically quite accurate as well. But the major part of the uncertainty comes from this 3 omega voltage measurement. As I told you before, the 3 omega voltage component is very weak signal, and even if we use lock-in techniques, there's typically some deviation in the values, even though we average the measurements for a long time. So we measure this 3 omega voltage component at different frequencies and determine the slope for this linear region of the measurement. And the linear regression fit of this data gives the largest uncertainty component for measurement of the thermal conductivity in this case. These parameters are uncorrelated, so that we can use this kind of equation for determining the combined uncertainty for the thermal conductivity measurement. And I guess this is a little bit more demonstrative way to show you what is going on, is to show uncertainty budget with the numerical values. This is an example of Wismut-doped lead telluride sample measurement, which was measured at 312 Kelvin. So we have the uncertainty sources here. The uncertainty due to the temperature dependence of the strip resistance measurement, uncertainty due to the 1 omega voltage measurement, uncertainty in the length determination of the length of the heater strip, uncertainty of the heater strip resistance measurement, and the largest part comes from the determination of the slope of this 3 omega voltage measurement as a function of frequency. For this sample at this temperature, we got expanded uncertainty of 0.16 watts per meter Kelvin, which means relative expanded uncertainty of 6%. We measured almost 10 different kind of measurements throughout this project, and typically the uncertainty values were between 5% and 8%. And it seemed that those materials that have higher thermal conductivity have also higher uncertainty. One reason is that for high conductive materials, the slope of this 3 omega voltage measurement, the slope is very flat, and it's difficult to accurately determine the slope of such a flat curve. Here's a list of properties of the 3 omega facilities that are used at MIGES at the moment. We do measurements in a horizontal tube furnace, in air, argon gas, or vacuum environment. Temperature range is from 300 Kelvin to 725 Kelvin at the moment. We are trying to increase the higher temperature part here, but it requires a little bit different kind of materials to be used. And thermal conductivity values, the measurement range at the moment is from 0.1 watt per meter Kelvin up to silicon value, which is about 150 watt per meter Kelvin. Finally, a summary. So the 3 omega method is an AC technique which is suitable for both bulk and thin film thermoelectric materials, but it can also be used for many novel nanostructured materials, for superlattice materials, for nanotubes, for nanowires also. And the benefit of 3 omega method is that it does not require accurate pre-information about the sample dimensions or other material parameters. It is relatively fast measurement and it can be used over a wide temperature range. Heat losses by radiation or through the substrate and wiring are small. The downside in this method is that it requires preparation of the sample, thin film buttering and microlithography. But on the other hand, we can use these prefabricated Kapton sensors so that they are transferable. We can use several different samples with one sensor. It makes evaluation of new materials much easier so that you don't have to deposit a heater strip on every new sample, but you can use the same transferable Kapton sensor instead. At the moment, the best measurement accuracy is about 5%, but with some modification in our system and with some optimization, we expect that we could reach a little bit lower uncertainty values. Okay, that was end of my presentation.
You said that you use this differential method to obtain the 3 omega component with the lock-in amplifier. Wouldn't it be better to have some mixing techniques or PLL to produce a real 3 omega reference signal for the lock-in amplifier?
Might be a good idea. We have been using this technique only now and not really considered other methods, but in future it might be a good idea to try different kind of methods to detect this third harmonic component. Yes.
Thank you.
Thank you. So the title is a bit cryptic here, if you look at, but there was a specific work package dedicated to nanoscale characterization of thermoelectric properties, and people from different institutions contributed to this work package. The objectives were to, as Frank has shown in his introduction, there's been
Okay. As shown in his introduction, that experiment have shown that nanostructured materials are better thermoelectrics. And there are various explanations for this, and it's still a bit not totally understood in terms of the physics, but one of the suggestions is that the interface in nanostructured materials may block some of the phonon, for example, so they have lower thermal conductivity, And another explanation, maybe they have a higher Seebeck coefficient, of power factors within the grain. So we wanted to see if we can develop some techniques to try to measure very locally these transport properties. Another extension is also that we need to know uniformity of reference materials and materials in general, and also in terms of measurement, because all of them are based on the scanning probe measurement, is the concept of having, touching your surface with a probe and being able to measure, in fact, three quantities, three measurements: the resistance, or conductance, the thermal conductance, and the Seebeck coefficient. So just to introduce the topic, I'd like to review very briefly what happened when we use the scanning probe methods, because it's fairly complex to understand or to model or to get accurate measurements. I mean, obviously there are a set of commercial instruments you can buy. It's relatively easy to get images, but to get quantitative data is much more difficult. So you have to, the principle is, if you are not familiar with it, is that you have a nanometer size probe in contact with the surface, and you will have some interactions, forces between this probe and the surfaces. And if you want to measure transport properties, you can bias your samples, for example, with respect to the probe. You can put thermal gradients. You can do whatever you want, really. And for example, in case of the electrical current going through these nanometer constrictions, the type of transport will depend on the Knudsen number. This is something well known for people doing vacuum, for example, and it's exactly the same concept here. And the Knudsen number is defined as the ratio of the mean free path of, for example, the electron, if we are talking electrical transport, and the radius of the constriction. So it seems a bit like weird to use this concept, but in fact, when you realize that the radius of the contact between the tip and the surface is in the nanometers, you realize that we reach a regime when we need to be a bit careful. So it's well known from the literature and from previous years that basically we have two regimes, what we call the Maxwell regime, the classical regime we all think about intuitively about. If you want another regime, which is Charvin regime, where the transport is what we call ballistic, meaning that we don't have scattering of the carriers, which could be electrons or photons, depending on what we're talking about. And because it is, we not only we have this transport and the mean free path and so on, but because we are at the nanoscale and we have a very small tip and there is, capillary forces, van der Waals forces, there is a range of forces that act at this scale, and it's become quickly very complicated to try to control all of them. And they will have important effects. So the best way to deal with this will be to couple the experimental method with simulation techniques, and they can be as sophisticated as quantum mechanical approach, or be more, continuum-based, like a finite element method. And that's the one we have used here, and it was done and essentially at CMI and the Czech Meteorological Institute. And what they've used is they've modified version of finite element solver called SphiPy, which is relatively unusual because it's a Python module. It's not something when you can have an interface, program your system and so on. But as a result, it's totally programmable and you have a very large flexibility. So you can put any input field in any configuration and try to measure what happened. It's very useful for scanning probe microscopy. So this is demonstration when you can change electrical potential, current, and so on. And so this software was modified to simulate the whole process of the scanning probe. So we can, in effect, simply send our image to CMI, and they can compute the different forces acting on these images. Okay, I'm going through these three measurements now. and make a conclusion at the end. You see it's pretty similar for the three measurements. For each measurement, I will do the same. I will tell you what method exists, maybe the problem there is, what we have achieved, and maybe some of the limitations, which, you know, it's not to say that it's never not going to work. There's still a lot of work to do if we want to have accurate measurements at the nanoscale. So for resistivity measurement, it was nicely, you know, nice review by Bernd, and shown how it is done at the macro scale, how difficult it is already. Obviously, the nanoscale has become even more difficult. But there are two techniques that are used, or people try to use, let's say, to measure resistivity, is the scanning capacitance, when you measure a vibrating probe and the capacity. And what you measure is, in fact, the carrier concentration within the samples. And if you know the relation between the carrier concentration and the resistivity, you know the resistivity. That's something we don't know really for the new materials we have. Usually we receive materials, we don't, you know, we know little about them. They have not been that well characterized, so it's a bit difficult to do that. Another method is called scanning spreading resistance, which is essentially current measurement, but at a very high force. And it's been developed specifically for silicon. So the high force is there, so you punch through the oxide. And then we have, basically, essentially, IMEC is produce a reference samples when you can link the resistance you measure at the given forces with the resistivity or the doping concentration of the layer. So if you have these reference samples, you can measure resistivity relatively accurately. We're talking, you know, 20% maybe. Obviously, we don't have this luxury here. We don't have a series of samples with known doping concentration and known resistivity. So, you know, and that's the fact for most of these new compound semiconductors that are used as promising thermoelectric materials. So nevertheless, we decide that we want to use scanning spreading resistance and current resistance because, you know, that's the most direct measurement. And the setup we used is described here with a little schematic. And we use conductive diamond tip. The reason we use diamond tip is they're very hard, so they will not wear away as we press very hard on the sample and we scan. They are highly doped, so their conductivity is pretty good. And we measure the resistance, if you want, between the tip and the bottom of the sample. There's a series of resistance in the instrumentation. They're all in series. But the measurement of the resistance gives us a combined standard uncertainty of 0.2%. So it's pretty good. But it is a resistance. You know, here the keyword is resistance, because if you want to go from resistance to resistivity, depending on the model, but usually it's more or less, inversely linear relation between resistance, resistivity, and the contact radius between the probe and the sample. And this contact radius, we don't know. And the uncertainties of the contact radius is enormous, and really could be 100%. So, you know, I can give you a resistivity that match exactly the value in literature because I choose the R accordingly. So this is an example of our results. So on the left here, we have the topography. It's still pretty rough. We've tried to improve this on polishing the samples, but we can still see local variation. And by the way, there are like 5 micron images. You can 10 micron, sorry. You can still see a variation in resistivity. And as an example, we have done a series of spectroscopic measurements to the IV curve at different points and so on. And we get a series of points and average value around usually between 30 or 45 kilo ohm as a resistance we measure. As I say, if we wanted to measure resistivity, we can try to develop model. We can try to have a contact mechanical model and mean 3 pass for the bismuth telluride. Depends of a lot of parameters that we don't know. So all these parameters are relatively unknown, if not totally unknown. When I look at the literature, they vary from a factor 1 to 100. And So the key message here is that you need to be careful when you see quoted resistivity with atomic force microscopy, because the value in resistance can be very reproducible, let's say within 5 to 10%. The resistive value is entirely dependent of the model, and the model contains a lot of uncertainty. Okay, so nonetheless, for example, we have here a little plot when we have demonstrated you can measure the variation in resistivity with temperature with the FM by doing average spectroscopic curve. So it's still pretty powerful as a technique, and you can use it as a relative technique if you want. Thermal conductivity, so this is the state of the art. If you want the different method, and for the bulk has been reviewed by Ossi and in his presentation. And there is still, what I'd like to point out when the methods that have been presented is that only in a sense the steady state techniques, the first one, you measure directly the thermal conductivity. All the others measure something else and will infer thermal conductivity using a model. Okay, so we need to be a little bit careful about this, and also there is often a lot of constraint on the geometry of the samples in this method, especially laser flash method. Usually they are done for 1 centimeter diameter and 1 5 millimeter thick film and nothing else, more or less. So this is a problem very often for people who want to use this method. In terms of nanoscale measurement, the original method were using Wollaston wires, really simple wires like 5 micron thick platinum wires clad in silver, in contact with the samples, and you can measure temperature by using these sensors as resistive thermal sensors. Okay, so most of the research or the publications in academic level have been focused on temperature measurement at nanoscale, which is quite interesting by itself. But here we wanted to try to see if we can look at thermal conductivity. And the probe we have used are described schematically here. They have been developed by Glasgow University recently, and their advantage compared to the Wollaston wires is the size of their tip. It's now nanometers, really. So this is a top view if you want, and I'll show you a side view. But you can imagine, this is the side view is a sort of board or springboard, large springboard with an electrode patterned on top, and here the red part is that it's all made of gold, the electrode, if you want. Only at the end is made of palladium. So this is the resistive element, and when you go in contact with the surface and you measure the change in resistance through this palladium filament, if you want, and this will give you a temperature, a relation with the temperature. So there's a number of assumptions. You need to produce a thermal model to try to understand really what happened at the tip and how the heat is related to the change in temperature. And we have developed this model. You can use it, it could be an analytical model, then you can transfer it to a finite element package like COMSOL, or in our case was done by CMI in their FEA model. And sorry, if I go, there's a missing sentence here. I just want to explain it, unfortunately, without the pictures. To measure the temperature, what we do is we put a very small current in this path, if you want, and we measure the resistance of the electrode, and the resistance is a function of the temperature. And there is not much, in quotes, it's a bit not self-heating of the probe. And to measure thermal conductivity, what we do, I think it's coming later. Sorry, it's here. So I just keep here and to show you. To measure the thermal conductance, because that's not the conductivity, we apply a large current. So we heat the probe by Joule effect, and we are in non-contact. And after this, we go in contact with the surface, and when we're in contact, there will be heat loss due to thermal conductivity between the tip and the samples. So now we measure the additional electrical power you need to put inside the tip to compensate for this heat loss. And this is equal to the proportional to the thermal conductivity of the thermal conductance of the samples. Again, I don't want to talk about thermal conductivity because of this relation with the contact radius. So in order to do that, I mean, the principle is pretty simple. The practicalities of it is a bit different. We need first to characterize the probe power and the thermal gradient we can manage within the system when we have the tip in contact with the surface. So this is what we show here when we measured, the resistance of the tip as a function of the temperature on this graph, or the current we need to, at constant voltage, we need to input into the tip to have a given temperature on the tip, as calibrated before. And this is the temperature as measured using standard thermocouples between, the stage, the top of the stage, top of the sample, the cantilever, and so on. The first thing we wanted to demonstrate, we are not going to talk about accuracy here, but it's about how repeatable the measurements are. The lens, okay, somebody is going to come with a clever model and give us a good value, but now we want to see how repeatability in the measurement is. So we have used a composites made of two thermal conductivity, two materials which are low thermal conductivity, so similar to thermoelectrics, and one is like polymers around 0.3, and the other one is our glass fiber, which has thermal conductivity around 1.3. And done a series of measurements on the samples and done analysis on the variation of the power required to have thermal equilibrium when we are in contact compared to when we are not in contact. And we have reproducibility in the results of better than 10% in all cases. Resolution, and we have to demonstrate lateral resolution in all cases. Now, I've not shown it before, but for electrical resistivity, but there is a definition in the ISO draft standard, which is similar, if you want, to what chemical analysis or surface analysis people will use. So you will need to measure a step and the step change, and you will measure the value at 10% and 90%, and this will give you the lateral resolution. So in order to demonstrate we have better than 50 nanometers, you need to scan small area with a lot of pixels and have an abrupt change in the surface. So it's pretty challenging to find. Once you have the image, the analysis is very basic, but you will need a very sharp surface and a very high resolution images to show that you have this. We have implemented this using this image here is a 3 omega methods to measure thermal conductivity. That's where at the end, we wanted all our measurement to be related to the measurement made by PTB for electrical resistivity or Seebeck, or MICES for thermal conductivity. So we have implemented in the FM a 3 omega techniques when we, input a sine wave into the tip and measure the third harmonic response. So we get some decent images using that, but we did not manage to complete, if you want, the loop and measure or infer the thermal conductivity to compare with MICES, unfortunately. The measurement, we have done measurement on thermoelectric materials as well. It's a bit more difficult, as you see the quality of the image not that great because the polishing of the surface, that we spend a lot of time between all the measurement to polish the surface, and the quality of the surface is obviously paramount when you do this nanoscale measurement. So I've done this. So as I say, we have demonstrated that in practice with the instrument we can reproduce the data each time we do a measurement. The accuracy of the value is an issue because we need a good numerical model. So there is a lot of work has been done by CMI to do a simulation of the tip resistance with the samples. This is an example of an image of the temperature distribution in the samples. And they are able, for an image, for example, when you have topography here in A, thermal conductivity, to deconvolute, if you want, the correlation between topography and thermal conductivity, because there is a lot of crosstalk in this. And this is very important in our measurement, because we don't know what if we measure topography or the thermal conductivity, and we need to go through this loop of simulation. Last one, and it was quite not the least one, because it was quite difficult. It was to try to measure Seebeck measurement. So the state of the art in terms of Seebeck has been reviewed by Ernst here, and they have fantastic reference materials. At the nanoscale, there is nothing. It's simple. There is a macroscale measurement system when they see a lot of variation in a series of materials, and this has been done originally at DLR in Cologne, in Köln, and I think there's another system very similar in Caltech now. So that's what we wanted to measure. So essentially, our system and our idea is to have as large as possible is to have a gradient of temperature between the tip and the bottom of the sample, and to measure the voltage between the bottom of the samples and the tip. So it's always, the idea behind IFM. We have this nanoscopic probe and the microscopic probe on the other side, and try to see what happens. Obviously, the distribution of the field may be difficult, but so let me show you what we've managed to do. We've first used the N-type bismuth telluride samples. It's provided by NIST as a reference materials. That's one the measurement we have managed, and we have seen that's what we are interested in reproducibility. So we have done a series of measurements. I'm just showing a few of them here. Essentially, so we measure directly the temperature gradient and measure the difference in voltage between low temperature gradient to high temperature gradient, and compute the slope to see what was the Seebeck, and we have a value of about 100 microvolt per Kelvin, which is less than half of the certified value by NIST, which by itself, is not a big issue, because we certainly have overestimated the temperature gradient, their heat loss. We have not taken into account certainly the tip will heat as it gets into contact. And we can demonstrate this, for example, on this graph here on the bottom right, you have non-contact measurement, and there the Seebeck is minus 150. It's much bigger in general, because we have less heating of the tip. But again, it's not that much the accuracy here, that the fact that it is relatively reproducible for different value, and each time you do the measurement for the same tip, you have more or less 10%. You have less than 10% variation. Just to demonstrate that we measure what we think we were measuring, because I was a bit worried that we measure, God knows, the tip variation as a function of temperature. I mean, we have tried to measure the resistivity of the tip variation as a function of temperature and so on. If you switch to a p-type bismuth telluride, we observe the reverse behavior and a p slope, which is a relief. But again, the value is not as accurate as we would like. And just to conclude and to show you the power of the method, and I hope this is visible, ultimately what we would like to do is to really image the properties at the nanoscale and to show how they vary as a function of the grain. So here on the left, we have an electron beam scattering diffraction image of the surface, and you can see grains, about 5 micron. And this is a thermopower IFM image done at 50 degrees C. And you can see some of the grains, and they look similar in shape and size as the EPST. We have also, sorry for the title here, we have also demonstrated that you can do that with a resolution better than 50 nanometers. So, and to conclude, I mean, there is a thermal simulation available for this type of techniques. When we see a lot of correlation between the topography and the measured voltage, again, So now the take-home message for simulation and from the experiment is if the gradient of temperature is large, like above, let's say 20 degrees in our experience, you will have a crosstalk between topography and the voltage or the temperature channel, for example. So in conclusion, what we have managed in this project and demonstrated is that the precision of atomic force microscopy or scanning probe measurement with the same tip is better than 10% in all cases, resistance, thermal conductance, and Seebeck. There is still a need to improve the measurement and the correlation with the model, if you want, in order to improve accuracy. So we need to do a little bit of work there. The lateral resolution is below 50 nanometers in all cases. I mean, it's just difficult to find the samples to prove that it's how low we can go, but it's always below 50 nanometers. And the good news is the sensitivity is excellent, and that's what IFM is used most of the time. You want to see local variation. Okay, the accuracy is not that great, but local variation you can see pretty clearly. And when I say excellent, it's maybe sometimes too good, so you need to prepare the samples carefully. And with this, I just want to promote this book, which is part of the project, or part of it is part of the project and was written by Petr and Klapetek from CMI, and will tell you everything you need to know in terms of the simulation and the artifact you may have in SPM. Thank you for your attention.
As thermoelectric materials or energy harvesters?
So for the materials themselves, the goal is to improve their ZT. So I didn't show it in the beginning, but if you look at Frank's slide, some of the nanostructured materials will have a ZT at least a factor 2 higher than normal materials. So and this only can open a lot of applications, because if we double the ZT, we can reach applications that are used now by other thermal process, or mechanical thermal exchange, for example. Or for example, we can use materials that are cheaper and easier to process. So the example I have in mind will be, for example, silicon. If we manage to somewhat produce silicon that they have a very high ZT, this will be great for the semiconductor industry. They don't have to move to something like bismuth telluride or some, difficult to controlled semiconductor compounds. So that's one of the main driver: increase the ZT, open new markets, or maybe improve the manufacturability of the existing thermoelectric system.
Seems to be not the case, so I think we can finish this workshop. I would like to thank the speakers for their talks and the attention.